So I want you to try and answer. If you haven't answered these questions here at the before you hit play on this video, please do that now because I want you to think about it. You can figure this out on your own. We kind of discussed it already, but now we're just formalizing those thoughts. So hit pause. How can we test whether f prime is increasing or decreasing? Well, to test if a function is increasing or decreasing, we take its derivative. So take the derivative of f prime becomes f double prime of x. So we're going to find f double prime. And I know if f double prime of x is less than 0, f prime of x is, whoops, that's funny why it does that. It makes these funny lines. Let's try that again. So if f prime of x is less than 0, then f prime of x is increasing. If f double prime of x is greater than 0, then f prime of x is decreasing. So if f prime of x is increasing on an interval, what can you conclude about f double prime? So I just kind of went through that. I know that it means f double prime of x must have been greater than 0. So if f prime of prime is decreasing on the interval, what can you conclude? Well, f double prime of x must then have been less than 0. So what is going on if f prime of x is equal to 0 on the interval? Not just at a point, but on an entire interval instead. What does that mean about the graph? So that means f prime of x is neither increasing or decreasing. So if a function is neither increasing or decreasing, f prime of x is a constant function. So for example, f prime of x could be 3 everywhere. So f prime of x could be equal to 3. Well, if f prime of x is equal to 3, I know that f of x was a linear function with a slope of 3, because this means that the slope is 3 everywhere on whatever interval we're looking at. So that must mean f of x was linear on that interval. Okay, that gets us to the test of concavity, basically what we just went through here. We just talked it out. So theorem, I put a little addendum to theorem. It's not in your books, but it's very useful to have that. So the test for concavity is let f be a function whose second derivative exists on the open interval, where the second derivative is greater than 0 on the interval. It means it's concave. The function is concave up. And if the second derivative is less than 0, it means that it's concave down. And that's basically taking the concavity, the definition of concavity, and applying it here. Because if I know that f prime of, if the second derivative is positive, the first derivative must have been increasing. And by definition, then that means that it is a concave up on the interval there, or f is concave up on that interval. Same if the second derivative is negative, that means that the first derivative must have been decreasing, which by definition is a concave down interval. All right. And then the addendum that I have is if the second derivative is 0 for all x's on the interval, then the graph is linear on that interval. So how do we apply the test for concavity? Find the critical numbers of f prime of x. Find x values where f prime of x is equal to 0 or does not exist. It just works exactly the same. So we're doing the things when we found increasing and decreasing on a function. We're doing essentially the same thing, but we're applying those rules to the derivative function instead. So use the x value in step 1 to determine test intervals, just like we would for increasing and decreasing. Use only x values in the domain of f of x. So look for asymptotes in some places, and it's going to be endpoints of test intervals as well, because behavior can change at an asymptote. So we need to find critical numbers and possibly asymptotes. A lot of times those asymptotes will show up in those critical numbers, but it's worth being aware of. And then test the sign of f double prime on in each of those testing intervals, just like when we did increasing and decreasing on a function. So let's try example 1. Determine the open interval on which the graph of f of x is equal to e to the negative x squared over 2 is concave up or concave down. So that means I need to really figure out the second derivative and then find the testing intervals to use. So the first thing we need to do is find the first derivative using the derivative rules. So give it a shot first. So remember, an exponential, especially when the base is e, is itself times the derivative of the exponent. So itself is e times negative x squared over 2, and then the derivative of the exponent is, you could have rewritten the exponent as negative 1/2 x squared, then becomes negative x. So I just polished it off a little bit, wrote it nice and neat here, because it makes it easier to take the second derivative. For the second derivative, you have to remember to use the product rule. So we're going to use the product rule to find the second derivative. Here, remember, you take the first times the derivative of the second. We actually did the exact same one there. And then the second times the derivative of the first. And then I polished it off a little bit, did a bit of factoring because it's much easier to find where the derivative is equal to 0 or undefined when it's factored. And then just like we did when we did intervals, here and now it's just this, when we did increasing and decreasing on intervals, it's essentially the same thing. First of all, f double prime of x is equal to 0 when x squared minus 1 is equal to 0. So that means when x is positive and negative 1. So that created my testing intervals here. So right here, I have my testing intervals. It's going to be, the endpoints are going to be negative 1 and 1. And then I'm going to just find values that are in each of those intervals. I picked negative 2. You could do negative 10 if you wanted to. And then 0 was an easy one in the middle interval and 2 on the other interval. And you just have to remember, the key is just the sign. So I'm not even bothering to simplify this. I can see that e to any power is going to be positive, unless it has a negative in front. But e to any power is positive times a positive. So a positive times a positive is positive. I don't have to simplify any further. E to the 0 power is 1, but times negative 1 over here is going to give me a negative. And then the last one, e to any power is positive, and then 4 minus 1 is positive. So that means those intervals are going to have a positive, a negative, and a positive in this case. So now all I have to do is draw my conclusions, because where the second derivative is positive, the function is going to be concave up. Where the second derivative is negative, it's going to be concave down. And where it's positive, it's going to be concave up. So there's a little memory device. I don't know if, first of all, let's make the conclusion here. Don't forget to write the function. You're describing the function. F of x is concave up. It's f of x, not f prime of x. F prime of x is increasing on the same intervals, but f of x is concave up on the interval from, so wherever you have positive second derivative, since the second derivative is equal to 0, so I'm justifying, right? And then f of x is concave down. Don't say it, the graph, don't be general about it, right? And there's, for some of you guys, if it helps, I don't know, for some people, if I draw two faces here. So positive is concave up. Negative is a frown, like that. That's concave down, right? So the smile is up, that's pluses in the eyes, and down you have the closed eyes with a frown. That's the negatives. I don't know. It's just a silly device that helps for some people. For those of you guys, by the way, taking stats, this particular function is very close to the normal probability density function. Those of you guys that don't, I taught stat for many years, so those of you guys that are not taking stat, it doesn't really matter so much. Just that you know that this function, if I drew this on the graph, and you can try it, is going to give me a bell curve. So here it just has a coefficient here and a slight difference, like this right here is the standard deviation, for example, right? The standard deviation is some constant for a particular function. And this here is still, so the whole coefficient there is a constant. It just stretches or shrinks the function, like how big the bell is. And the same here, it's just going to be a slightly different constant there, but the basic shape is going to be the same. So this here actually is how you prove the normal probability density function, or how you develop that in statistics, just out of interest.